Okay, so what I talk about today is called image restoration. Okay, so image restoration is, again, a way of making an image look better. And in general terms, we already talked about this a little bit. So we've kind of talked so far about improving the visual quality of an image. And so some of the things we talked about to this point include, if I've got a noisy image, I could do low-pass filtering or spatial averaging to remove something like Gaussian noise. We talked about median filtering to remove impulsive or salt and pepper noise. And we talked about things like unsharp masking to enhance details. And so now what I want to talk about is this process of, how does an image get corrupted, and how can we undo that corruption in a little bit more mathematical detail, okay? So the difference between what I'm going to talk about today and what I talked about before is that these things are still something that you kind of fool around with by eye to try and make the image look better to you as a human, okay? But by the same token, there should be a way to automatically attempt to undo the corruption that was done to an image if we knew how it was corrupted, okay? So the difference between today and before is this is like objective image restoration, and before we were talking more like subjective image restoration, okay? And so today is basically objective methods for undoing corruption. And so let's be a little more specific about what kind of corruption I'm talking about. So the basic model that we're going to talk about today for, I guess maybe I should call it degradation, is I've got an image. It goes through some sort of a degradation filter, say like a point spread function. Let's call that H, okay? So this is like a linear system that is, think of it like a blur, okay? So I'm just going to put in the box like blur, for example. Okay, so now I've got a blurry image that comes out of here. And on top of that blurry image, I'm going to add some noise. Okay, so what comes out is some degraded image. And what I want to do is now I want to put this degraded image through some sort of a restoration filter. To get some output that is hopefully as close as possible to the original input, for example, in a least squares sense, right? So I want the sum of squares of this minus that to be as small as possible, right? So that's a mathematically well-posed problem that I should be able to find the optimal filter to solve, right? And so in the spatial domain, the degradation looks like this, right? I have my original image, and I am convolving it with some 2D impulse function, or impulse response, and I'm adding noise to it, right? And in the frequency domain, I have the convolution turning into multiplication, and I have some additive noise here, right? And so the idea is that a lot of times we solve these problems in the frequency domain because of the way that the multiplication becomes convolution, okay? And so this is one of the reasons why we talked about the 2D Fourier transform, several weeks ago, was that restoration filters typically involve Fourier transforms, okay? So we're going to work mostly in the Fourier domain. Yes?
Convolution or circular?
So this technically would be the kind of normal linear convolution, right? Because there's no reason why, when the image is degraded, that things would wrap around the edges. So I mean, the kind of way I think about this is that it's linear convolution that I could model as circular if I padded the image by a few zeros, right? Yeah. So don't worry about the linear circular thing too much here. Okay. So the easiest case is when there's no degradation here, there's no blur. So this is like the identity function, and the only thing I'm doing is adding noise, okay? So the easiest case, or the easier case, is that this basically means, you know, I'm not actually doing anything to the image before I add noise to it. The degraded image only contains additive noise. And so noise is typically characterized by a PDF, right? A probability density function. So noise is typically described by a PDF, or technically a PMF, probability mass function, where I have a probability that the noise is equal to some value, right? And I usually assume that the, you know, noise is independent in every pixel, which is usually a pretty good assumption for images, although we talk about relaxing that in just a second. And so why can noise happen? Noise may be due to, I could have basically non-ideal sensor elements, meaning that, you know, there could be, you know, kind of, I could have a crappy camera that I got from a Happy Meal, and it doesn't have very good sensors, and so what I think I'm getting is not a very good, accurate estimate of what I should be getting. I could have environmental conditions. So, for example, as, you know, the light level or the temperature changes, I may get noise in my system that depends on that slowly varying environmental condition. Or I could have basically, you know, corruption during transmission or coding or compression. Right? So for example, we talked about last time how doing lossy compression, I'm basically taking the error, or I'm taking the, you know, the DCT coefficients, for example, and I'm rounding them, right? So you can think about the difference between my old image and my compressed image as an additive noise, if you wanted to, right? You can kind of try to model that noise if you wanted to. And so we usually assume, like I said, we assume this noise is i.i.d, which stands for identically and independently distributed. So the main thing I want to talk about with respect to noise is how do you know what kind of noise is added to your image, right? Because usually in the real world, you just receive some image, and if I want to undo the noise, first I have to have a good model for what that noise was, okay? So in some cases, right, so for example, if I'm talking about a transmission line where I knew what my original great image looked like, I sent it across the communications channel, I got my corrupted image, then at least I could say, okay, well, I knew what I had before, and I see what I have now, I can see exactly what the noise was, right? But in some cases, all I may have to deal with is the piece of image that I have. So I'm going to show you just one simple method for how you might be able to estimate that noise in just a second. But let me just say a few words about common PDFs for noise that you might see. So common noise PDFs. Well, the most common one that you're going to see is Gaussian. So Gaussian noise, basically, the model is this guy here. And it looks like, you know, some nice bell curve that is centered around the mean, and often the mean is 0, right? And so Gaussian noise is basically something that is well characterized as like thermal noise, sensor noise. Gaussian is usually a pretty good model for the noise. In some sort of applications like range imaging, so there's something called Rayleigh noise. So it kind of looks like a Gaussian in some region, and at 0 when I'm less than some value. So it's kind of like something that is 0 up to some point, and then has some sort of kind of looks like kind of a one-sided Gaussian that's truncated. And so this kind of noise occurs, for example, in applications like range imaging. So if you're sending something out into the world and it bounces off an object and then it gets kind of corrupted as it comes back to you, this is the kind of noise that sometimes models that. You may see some sort of exponential noise. And so that is kind of like, you may remember this from when we talked about it in probability. This is saying that the noise is more probable at low values of z, but there's no probability of getting positive noise. This sometimes comes up in things like laser imaging. Salt and pepper noise, we talked about in the context of median filtering, is basically like, I've got some probability of white, probability of black, and 0 else. So kind of what salt and pepper noise looks like is I have kind of like two delta functions. They're kind of telling me, okay, I have a probability of flipping a bit, yes or no. And then you might have, we talked about the uniform distribution. The uniform distribution, I'm running out of space here, so I'm just going to draw it like this, right? That doesn't really happen that much in practice, so we're not going to talk about that much. Salt and pepper noise often occurs with like faulty components. You may see some, bad circuit may freak you out. Okay, and so I don't want to do it right now, but if you look in the book, for example, you can see pictures of how the different noise distributions affect the image that you've got, right? So it's also possible to have periodic noise. So these guys all assume that the noise that's at every pixel is basically, independent at every pixel, right? But it is possible to have some sort of correlated noise. And so here's an example of, so I found a good website from another professor that I'm going to put online. But here's an example of noise from like a satellite image where clearly there's some sort of a regular thing that is causing this image to be corrupted, right? So there's definitely a spatially dependent periodicity that means that things are not happening, independently at every pixel, right? So this noise should manifest itself pretty clearly in the frequency domain, okay? Actually, let me just talk about that for a second since I'm on this image, okay? So what would this look like? So I put together a little demo. So I don't remember what my demo looked like. Always turn the warnings off in MATLAB. It can only hurt you. So, okay. I don't remember what my number was here, but we'll give it a shot. Okay, so here's this example. So here's my original image, right? And if I look at the Fourier transform of this image, I should expect to see, the usual kind of thing where I've got, disregard this weird thing that's happening on my screen because that's this is just the cursor for the input, right? Okay, it's going to say, what the heck is that? All right, so before I do that, let me just say, let's look at, let me Control-C this. So let's look at the FFT of that image. Yes, let's look at that way. So here I can see the usual kind of, intense in the middle, not so intense in the background FFT. But if I were to zoom in, and this is again kind of a gamma problem, but let me kind of zoom in a little bit to see if I can find where the problem is with this noise. Okay, so here, there are these two weird pixels here, right? Normally, the background here looks pretty much like grainy, uniform noise. But here, there are these two white pixels that are kind of out of place, right? That means that there's a lot of high frequency, there's a lot of contribution to those frequencies, whereas all the neighbors of this frequency seem like not much action, right? And that's what's causing that periodic noise. What I could do if I wanted to would be to try and just isolate those two guys, and since I have no other thing I could do, I just turn them into zeros, for example. So that's what I'm going to do here. I'm going to basically do what's called a notch filter. And so kind of the idea here would be that periodic noise, which is non-i.i.d, manifests as unusual peaks in the FFT. And we can remove these with a notch filter. And so the sketch would be that you would expect to see some sort of a weird peak here. And what I could do is kind of design a filter that was 1 everywhere across the frequency domain and just like zeroes out right above where that bad thing is, for example. Or I could do something, I think what I did in my MATLAB code is very simple. I just kind of drew a ring like this, and I just zeroed out this entire ring because I was too lazy to independently notch out each of the things. Or you could even try to take this and you could try to interpolate over that thing to fill in what might be missing. So let's just see what I do with my notch filter here. So So here what I'm going to say is, here's my FFT. Kind of hard for you guys to see here, but I can see it on my screen that, actually when I make this bigger it's harder to see. So I can see these guys here. It's probably hard to see on the screen here, but there are two little dots. So I'm just going to click on these dots here. So you can kind of see that there was this, this is my notch filter, which is basically 1 everywhere except for the narrow band around where I clicked in the frequency domain. And then when I take the inverse FFT of multiplying this together with this, I get this, right? So I mean, I've really taken away a lot of that, periodic noise. In some sense, it's surprising that I was able to undo the noise as well as I did. But that's because this is kind of a well-constructed example where I had inserted noise in a certain place and I removed it in a certain place. And you can see actually that, it looks pretty good. You can see there's a little bit of maybe artifacts like in these fields. There looks like there's a little bit of rippliness or something like that may be caused by, I didn't click in the right place or I didn't make my bandpass filter wide enough or something like that. But I preserved both low frequencies and high frequencies, right, because I was only removing noise at a certain ring, okay? So that's kind of fun, and that's something that you might find useful in your life one day. Okay, but let me say a little more about, if I'm in this case, where I've got just general noise, how do I know what kind of noise I have? And so, how to determine what kind of noise is present. Well, the easiest way is to say, okay, maybe I don't have access to the original image. All I have is this image, right? So what I could do is I could select a flat region of the image, a region that I know should be basically constant intensity, and then I could look and see what the pixels actually are in that region, and that should give me some hint as to what I think the variance or the PDF of the noise is. So let me show you an example. So let me just write down what I'm going to do. One way is to find a region that should be flat, which would be constant intensity, and look at the PDF. So let me show you what I mean. So So here's a real example. So this is an image of the moon that one of my grad students a long time ago took through a telescope. And so this is an actual image. And so here, this is an image I'm going to try as a running example to make it a little bit better, okay? So one thing is that it's a little bit blurry and it's a little bit noisy. And so here's what I meant about taking a flat region, right? So if I look at this region here, which is, kind of like one of these, seas on the moon, I can see that instead of being constant, it's got this kind of, noise. If I were to kind of zoom in on just the constant region, I can see that part of it is due to compression artifacts, right? So actually, if I zoom in, I can see this is a JPEG image, like we talked about last time. I can see little bits of JPEG basis functions, but also it's noisy just in general. And so here is my little algorithm for estimating the noise. So I wrote a little function, which is what I do. So here all I'm going to do is I'm going to use my mouse to click around click around a box of something on the image. I'm going to look at the histogram, and then I'm going to take the mean and the standard deviation of the intensities inside the histogram and fit, in this case, a Gaussian to the image histogram and see how good it is. Okay, so I guess I have two E's in noise est. All right. So here's my cursor again. So I'm going to kind of click and click. And here what I see is that the black is basically a bar graph that is actually the true intensities inside that box. And the red is a Gaussian distribution that's fit to those intensities. And I can see that actually the fit is really good, right? And if I look at my MATLAB output, which I neglected to store, I guess I can actually do this one more time. So what I want to get out is the mean and the variance of the noise. So I guess the mean is about 50, but I didn't get the variance out. So let's do this again. So here it is again. And mu and sig. Okay. So this tells me that the mean was about 50, which means that that was probably the true underlying intensity of that piece of the moon, right? And then the variance is 3.6, or the standard deviation is 3.6. That tells me that that's basically the width of the Gaussian that was added. And I can kind of see, one thing I don't know, I guess, is looking at this picture, I don't know, for example, whether or not the mean of the noise was actually non-zero, right? For example, that patch of moon could have been darker than 50, but actually was added to by this mean that was non-standard at zero. But let's assume that the noise is zero mean, because that's usually the way it would work in practice. Okay, so now I've got a model for what my noise looks like. And we're going to come back to that a little bit later. So let me just say on paper how this would work. So what I do is maybe a better way to think of this is look at the image histogram inside that block. I have a bar graph of actual values, and then what I could do is I could try to fit a PDF to that, right? And so, for example, the mean, the estimated mean, would be just the, I take the pixels in the block, and I take the probability of seeing each of those things, and the variance would be just the usual estimate that we talked about, like this. This is just from probability. How do you estimate the mean and the variance from a sample distribution? Okay? And so, it could have been that when I did my, when I showed my image histogram, maybe instead of getting Gaussian noise, I would have seen a PDF that looked a little bit different, right? I might have seen a PDF that looked more like this, or a PDF that looked more like that, right? And that would tell me, oh, I think that my noise model is exponential, or I think it's railing, right? So that's a good way to kind of estimate what happened to your image, okay? And so now let's think about, okay, so now the situation is that I've got my corrupted image is my original image plus this noise. And in the frequency domain, kind of similar. So here, this is where the unfortunate part is that, I can't just subtract this. Right? Certainly I can't do it in the spatial domain because I don't know what the actual noise pixel that was added was. And unfortunately I can't really do it in the frequency domain either because there could be image content at a given frequency bin as well as noise content, right? And so the only way that I can really do well on getting rid of frequency domain noise is if it has that kind of sharp peaks in the frequency domain like we saw for the periodic noise. So unfortunately, in the i.i.d. case, there's not much that we can do beyond what we already know. That is, we know about things like the mean filter. Let's see. It's like a really bad way of writing this in my notes here. So the mean filter, for example, could be something like I take my output at xy is going to be the sum of what I could do is I could say, okay, I'm going to take an n by n block around xy, and then I'm going to take those values and average them, right? That's like an averaging filter, which is something more than kind of saying I've got a spatial filter that's just, ones of n over n squared, right? So we already knew about this filter in terms of trying to take a noisy image and smooth it, right? And there are some variations on this, right? So instead of using a arithmetic sum, I could use a product and do a geometric mean. That also sometimes helps. And you also know about the median filter, right? So so I don't want to go through those again. So we already kind of learned what the what the best thing to do or what a good thing to do would be for additive Gaussian noise versus additive salt and pepper noise, right? And unfortunately, there's nothing that mathematically tells me what is the right size of filter to use to mitigate my noise. This is kind of like where I can stop in this case. The more interesting part of the lecture, which I'm going to get to next, is what happens when I've got blur plus noise. And in that case, I can do better than this in terms of a principled mathematical thing. So one thing that's a little bit unfavorable about the case of just like applying this single spatial filter across the whole image is that this is definitely going to be a smoothing filter, right? So it's going to take things that used to be nice and edgy in the frequency domain, it's going to smooth them out, right? One thing that you could do that's a little bit better than just kind of uniformly applying this filter across the whole image is to look locally at every pixel and think about, okay, so, I want to know at this pixel, should I be applying a aggressive smoothing filter, like if I'm in a flat area to make that flat area better, or if I'm in an edgy region, should I apply a less aggressive filter so I don't blur over the edge, right? And so kind of a better method is what I would call an adaptive filter. So this is going to change depending on the noise characteristics in a local window around a pixel. So what do I mean by that? Well, so let's suppose we know the corrupted image. Let's suppose that we know the noise variance across the entire image. And then we can estimate the local mean around a pixel. Let's call it xy. And the local variance. Okay. And so consider this as a possible way of doing reconstruction. So let's suppose that I say that my reconstructed image is going to be my corrupted image minus this. Okay, so we'll write that down for a second. I'm going to take a swig of Gatorade. So yeah, what we're doing here is we're going to make kind of a decision that's based on comparing the local variance to what I think has globally been added to the image, right? So let me scroll up a little bit. So if the noise variance across the entire image is 0, then that's like saying that my reconstructed image is the same image that went in, right? Which is kind of what makes sense, right? That's like saying that if I tell you I don't think anything was added to this image, then you shouldn't do anything to the image, right? Just return what came in, right? So this does the right thing when the noise variance is small. If the local variance is a lot bigger than the global variance, then what happens? Well, then this number here is almost equal to 1, right? I'm sorry, no, then this number here is basically almost equal to 0, right? That's like saying that the denominator is much bigger than the numerator. So that means this whole other term goes away. So that means that my estimated output is pretty close to my estimated input. And so why is this good? Because a high local variance probably means an edge is present. And we want to preserve edges. Right? So if you remember from when we were doing, looking at edges, an edge basically comes about when I have a lot of pixels on one side that are dark and a lot of pixels on the other side that are light. That means I should have a pretty high variance in that region, right? And so I don't want to blur out that edge. I want to keep that edge as it is, okay? On the other hand, if the local variance is about the same as the global variance, then this number is 1, which means that this is saying take this, subtract this, and then just add the mean. So that means that my estimated output is going to be basically the mean. And so this is like saying, average intensities in kind of normal regions. Right? So it's like saying, if nothing unusual is happening around this pixel, then just kind of give me the mean around that pixel, right? But if I've got an edge, keep that edge. So this will, on the average, do better than just applying the same averaging filter to the whole image. The drawback of this whole thing, obviously, is I need to have this estimate of this global noise, right? So we need an estimate of this global noise variance for this to work. But I just told you a method for trying to estimate that, right? E.g. from the previous method, right? So for example, here in my moon example, that's exactly what I just did, right? I just got this estimate of the variance, right? So sigma squared is about 13, right? So now I can use this number to say, okay, if the local variance inside a block is less than 13, then, or is around 13, keep things happening the way they are. If it's much greater than 13, take the average. And so luckily MATLAB has a built-in function for this called Wiener 2. So this is exactly the algorithm I just told you about, where I supply a noisy image, I supply a block size, it tells me kind of where do I define my neighborhoods, and I have to pass in this noise, which is basically the estimate of globally how much noise has been added to the image. And if I don't do anything, Wiener 2, or if I don't supply that noise, Wiener 2 does its best to estimate it, okay? And so let's just apply this to my moon image. So I got my noisy image. So again, I don't have the original image, so let's take my new image and apply this with, say, I don't know, 9 by 9 blocks. And then I believe I have to supply the variance of the noise, which I'm going to say is 13, for example. Let's make sure I did that right. So noise, yeah, so it should be 13. Okay. And so, oops. So this is my original image. This is my fixed up image. And let's see how they compare. Well, that looks great. So what did I do wrong here? Oh, I actually didn't supply the image to my Wiener function, which is probably important. How do we do here? Okay, better. Okay, so figure 1 should be before and figure 2 should be after, I believe. So here, I can definitely see that I have smoothed out the image, right? In fact, maybe I was a little bit too aggressive here. It does look better on my screen than on the projection for some reason. Let's try zooming in and seeing something here, like here versus here. Right, so here you can see that I definitely mitigated the noise inside the image, maybe a little bit too aggressively. But on the other hand, the boundary of the moon, right, is not very much blurrier than it was before, right? So it's kind of like I've kept this sharp black to white boundary, but I've removed the noise in here. And I wonder if there's a function, if there's a command I can say to Wiener 2 to be a little bit more gentle. Or maybe I used a window that was too big. So let's try what would happen if I used a smaller window. Okay. So I want to go to this guy. So let's zoom in here again. So this actually looks a little bit better. Right, so this is kind of like the before and after, right? So here, this is probably a better example than what I showed before because I think I used too big of a block size. So I've kind of definitely smoothed out this noise that was present inside this C before, but the overall sharpness of the boundary here looks pretty good. And if I try to find something that's a little bit sharper, like for example, let's try like here. I haven't really lost that much detail in the image, but I have gotten rid of this kind of crummy, noise, right? Because there's not really that much comparative noise over here. So, it's not perfect, but I mean, even visually here, you can see that the image on the left-hand half of the moon is a lot noisier than it is on the right-hand half, right? And if I was to just, for example, uniformly apply, let's compare this to, okay, so let's compare this to a filter where I just smooth the image uniformly. So let's say I applied the image with a smoothing filter. I hope this will bear out my point, otherwise I'll look stupid. Make sure I actually showed the right thing. Yep. So kind of what I want to see is how does this compare to what I had before. So on the left is my, adaptive filter, and on my right is a smoothing filter. I guess it's kind of hard to say. I mean, actually, this seems still a little bit noisier. And this is kind of a thing where I could tune the block size a little bit. If I were to spend more time on this example, I could probably do a better job. Anyway, so it's actually kind of strange. I wonder what happened over here. Oh yeah, I want to talk about this guy here. This is a star in the background. There's so much crap on my monitor that I can't actually distinguish the stars from lint, which is a problem. Okay, so both these stars are red. Okay, so let me talk a little bit more about what happens when I have actual degradation. Okay, so let's go back to the original image. And let me look at the star that I was trying to find before. Okay, there it is. I really should have wiped down my monitor. Here we go. Okay, so here basically is this, bright object, right? So in theory, this should appear in my image as a single bright pixel, right? I mean, a star is infinitely far away. It should project to basically just like a nice bright pixel, or maybe at best a circular pixel onto my image. But instead, I get this kind of smear, right? And this is a clue that tells me that the image was blurred as well as noised out, right? Because I kind of expect this to be a nice sharp point. Like when I look in the sky with a telescope, I see these nice sharp stars, right? And so this is a clue that helps me de-blur the image. And so let me talk a little bit about this de-blurring process. So what happens when we also have degradation? That is, my degraded image is my original image convolved with some impulse response plus some noise. Here, again, in the frequency domain, I have multiplication instead of convolution. And so the most common thing is that this is some sort of a blur. Okay? So that could occur, for example, because I've got a crummy camera, I jiggled it while I was taking the picture, or there was motion of objects in the picture while I was taking the picture, also could be a problem. And so how could we estimate this blur? Well, I kind of gave you the preview already, so how to estimate this guy here. Well, there are a few ways to do that. None of them are like super satisfying because really all I have is the noisy, blurred image. Right? I don't actually have access to the original image. But let me talk about how that might happen. So one way is the highly technical way of guessing. For example, take a piece of the degraded image and guess what the original image should have looked like there. Right? And so then I kind of say, okay, I'm going to take my image block around the so here this S is equal to the guess area. So what I can do is I can say I'm going to look at the Fourier transform of that versus the Fourier transform of my manual guess. And I'm going to estimate that my overall blur in the Fourier domain is like, it should be basically the corrupted thing over the guess that I have, right? Because it's like saying that my hypothesis is that this crappy version of it was produced by convolving the ideal thing with the frequency response of the blur, right? And so, how might I do that? Well, for example, if I was taking a picture of something where I knew that there was an extremely sharp edge, right? So let's suppose that there was a wall here, and I knew that it was very likely that this side of the wall was black, and there was a sharp edge, and then this side of the wall was white, right? So it might be easy for me to kind of guess what the true chunk of texture would be in some regions of the image. I'm not saying you can do this for every region of the image, but for some regions where you have a pretty good mental model of what you should expect to be seeing there, maybe you could get away with this kind of hallucination of what the right thing should be. A better thing to do, obviously, is experimentation. And this is like if you have access to the imaging device. Which is along the lines of directly acquiring the impulse response or the point spread function. So for example, what I could do is I could say, okay, I'm going to put my camera in a very dark room. I'm going to turn on just like a pinhole of light that should be basically the equivalent of an impulse. That's kind of like, it's the same thing if I wanted to acquire the impulse response of a real audio system, right? So what I would do is I would, people go into churches, if they want to acquire the impulse response of a space for doing acoustical modeling, they'll basically set off they'll hit a thing with a hammer, bam, and that acts as an impulse. Then they record what they get, and that tells them what the impulse response is, because you're basically feeding an impulse into the system, and you observe what the output is. So you can do the same thing with images, right? You could say, I'm going to take a picture of a very bright light, very localized light, and what I see is going to be like a kind of a smeary version of that, and that's exactly what the impulse response of the camera is, right? So if I have access to my imaging device, and I can take pictures of whatever I want, then I could, in theory, kind of directly acquire the impulse response. Or, I could simply estimate or model this thing. For example, I could just say, okay, I assume that there is some Gaussian blur. Or I assume that if the camera is moving in a certain direction, I can generate the corresponding impulse response. And so one of the homework problems is going to be basically to have you take an original image, blur it with a known blur, and that way you know exactly what this thing should be, and you can undo it, right? So, in some sense, question?
Can we do it by just taking multiple pictures of the same thing and seeing what the noise response does from there? So instead of taking one picture of the
So taking multiple pictures in a row is going to be good for mitigating the noise, right? But I'm not sure it gets you any closer to knowing the impulse response of the blur, right? Because I'm going to basically get 5 blurry images, right? And they're all going to be blurred in the same way. That's kind of the problem, is that the noise is assumed to be different every time I take the image. And that's why when I take multiple images, I can kind of average out the noise, right? Because I expect that to be zero mean. But the blur is kind of more inherent to the imager itself. So I don't really gain that much by taking a whole bunch of blurry pictures, I don't think. So let me just say that this experimentation step is kind of what I was trying to describe when I was showing you that picture of the star, right? And so if I go back to this picture, this is really like the closest I can get to estimating what the point spread function might be for this, image, because I know that that ideally was an impulse that was shown to the telescope, right? And so my function here that I wrote is very simple. I call it get point spread function. All it does is it asks you for an image, it lets you zoom in on it, and then you crop out a piece, and that corresponds to the point spread function. So super simple. So in my case, let me just apply that here. So now I have to zoom in on this a little bit. Okay, so all I'm going to do is I'm going to say, okay, this is my point spread function. I'm just going to crop it out. And I'm going to use this in a couple minutes. So if I were just to look at this thing by itself, it's super tiny. But it's exactly the little star that I notched out. Okay. So now this is going to be my little estimate of what happened to blur the moon. Okay. So now from kind of first principles, the natural thing to do is to say, okay, so we have the degraded image. Here. We have the blur, which we suppose we got from somewhere. Which I'm going to call H. And either of these things that we thought about in the frequency domain. So then the most natural thing to try first is called inverse filtering, which is basically saying that my reconstructed Fourier transform should just be the Fourier transform by corrupted image over the blur that I estimated, right? So that makes sense, right? That's like saying, well, if I knew how the image is corrupted, I should be able to uncorrupt it by using the kind of inverse of the blur, right? So this sounds good in practice, but unfortunately it doesn't work so well or it just sounds good in theory, but it doesn't work so well in practice. And so let me show you what happens here if we try that with MATLAB. So there's a function called deconv WNR, which is, we're going to talk about the Wiener filter in just a second, but this is the idea is to say, okay, I'm going to supply the image, the estimated point spread function, and then I'm going to show you also need to do something about the noise. But for the moment, let's assume that the noise is 0. And so here this says specifying 0 for the noise is equivalent to creating an inverse filter. Okay, so let's suppose that I just try to undo the noise with my image and my estimated point spread function. I guess I did mean that, yes. Okay, so drum roll. Looks awful, right? So actually this looks like much worse than my original image did. Like all sorts of crazy, crappy noise, right? High frequency stuff. Looks like I just totally screwed up this image, right? So why is this happening? So, yeah, sorry, the sun has destroyed the moon. So the problem is that this usually is bad. And the reason for that is that actually this thing here, right, is, not just the original image convolved with H, right? So the model before was that I had my ideal image multiplied by H, and that when I divide by H, I should be able to undo it in the frequency domain. The problem is that there's also this noise, right? And so the noise is what's going to cause a big problem, right? So then when I undo this, sure, in theory, I get the original image, but I also get the noise over this H. And the problem is that, for example, if this H here is very small for some parts of the frequency domain, then 1 over that very small number is going to blow up to infinity, right? And so we know, for example, that a Gaussian blur, which is more or less like what that star was, like it's kind of like a little Gaussian, that's going to mean that there's going to be a Gaussian in the frequency domain, and there are some places where that Gaussian is going to be very small, right? And so when this is very small, as it's likely to be, then the inverse filter can totally blow up, right? So this is the issue, is that, I'm going to kind of write over here, if H of uv is very small for some uv, then this ratio can be very high. And that leads to, extremely poor reconstruction. So there are some mitigation issues. There are some ways we can attempt to mitigate this issue. So one is to say, for example, okay, I'm only going to apply this, filter in places where I think the filter has some sort of content to it, right? Close to low frequencies. And so one possible solution is only apply the inverse filter for low frequencies. And so that would be something like saying that my estimated output should be equal to the inverse filter for, some sort of radius that's close to 0, and and keep what I had before if I'm outside that radius. And probably what I want to do is kind of have a smooth transition between these two as opposed to just kind of like a step function. But this is the idea, right? Saying, inverse filter the low frequencies where I expect there to be problems, but for high frequencies where the noise over the H could blow up, just leave that the way it was, right? Then you're kind of stuck with tuning this, radius to be the right thing. So the right thing to do, which is something that we talked about in DSP, is what's called the Wiener filter, okay? And so there was a whole lecture back in DSP where I talked about the right thing to do. And so and by the right thing to do, I mean that it is what's called the minimum mean square error filter. So what I want to do is I want to take the error, which I can model as the expected value between my original image and my reconstructed image. What happened? Oh no, freeze. That's interesting. We had a crash. for some reason. Wonder if I'm still recording. Okay, sorry about that. So you didn't miss much. What I was saying was that the right thing to do is what's called Wiener filtering, which means that I have an error, the expected value between my original image and my reconstructed image. I want to make the sum of squares, I want to make that expected value as small as possible, right? So I have a model for how the corrupted image was produced from the original image, and we showed there was this thing called the Wiener filter. I'm not going to prove this, but it is as follows. So what I do is I take my reconstructed output as, and I'm just going to write this down. I'm going to write this down, and then I'm going to explain it. And actually, I'm going to write this in a slightly different way while you guys are writing that down. All right, I'm going to take a swig of Gatorade while you guys are writing. I was hoping to get through this whole thing, but I guess I was talking too much. Okay, so what are we looking at? So what's happening here is I have the h, which is my point spread function. I have these numbers at every uv. One of them is the power spectrum of the original image. One of them is the power spectrum of the noise, okay? And so this filter is, again, I'm multiplying, this is the corrupted Fourier transform. This is something I'm multiplying by that Fourier transform, and let's think about what's happening, right? So here, the problem before was that if this was 0, so if I didn't have this part, it would just be like the inverse filter, right? But you can show that this thing dominates this thing. So basically here, if this is now 0, if the blur PSF has 0 somewhere in the frequency domain, then this whole thing is not going to blow up, right? Which is good. I basically ensured that I don't get something that happens really bad. If the noise is known to be 0, then basically this term goes away, and this term turns into 1, and I just get the inverse filter. So if I have no noise, then I get the inverse filter. If I do have noise, I have something that's kind of getting close to the inverse filter, but doesn't have the bad numerical properties that the inverse filter does, right? So the problem is that there are some things for the Wiener filter that I have to know that I may not actually have access to, right? So again, the power spectrum of the noise, in theory, I could take my flat region of the image, I could estimate the noise, and I could get the noise PDF, and then I could estimate that. Or I could just assume this is basically constant. That's one possibility. That would be like the equivalent of saying I have white noise. The power spectrum of the image may be hard to estimate because I don't know the original image, right? That's part of the problem, is that it requires something I don't have access to. So kind of in practice, what I do is I try to tune this number to kind of match up to be what I kind of estimate the signal to noise ratio to be. So let me say that in a different way. So So we may be able to estimate the power spectrum of the noise, but we don't know the power spectrum of this because it requires the original image. Instead, we usually use something that's a little bit simpler. We basically say something like, I reconstruct my image as, I'm just going to rewrite this guy here. I usually have this tunable parameter, which I'm just going to call K here. And so K basically is like a tunable parameter that's related to my estimate of the signal-to-noise ratio. And I kind of tune this to give me a good result. And so the Wiener filter can do a surprisingly good job of improving images that are both noisy and blurry. And so now what I want to do is I want to tie this all together and say, let's look at our moon example again, which I know is noisy because I saw it in that flat region. I know it's blurry because I saw that star, right? And so now what I can do is Wiener filter that image to try and make it look better. And so here, if I look at my documentation for deconv WNR, you can see that it's asking for the point spread function, which is the H part. That's what I know from my star. And it's asking for basically my noise to signal power ratio, which is like that K in the previous slide. Okay? And so if I know more information, for example, if I actually knew something about the original image, here, if I had more information, I could do even better. But let's try it with the moon. Okay? So all I'm going to do is I'm going to do deconv WNR with the image, the point spread function, and now I can try basically estimates of this noise to signal ratio. So here I'm just providing a number for that K. So this number is pretty small, so that means it's kind of close to the, let me show the original image and this Wiener filtered image. Okay, so this is not so great, right? This is basically pretty close to the inverse filter, right? Because I am underestimating how much noise there actually is, right? So maybe I should try a number that's a little bit bigger. So let's try like 10 times as much. Yes. I did mean that. Okay. Things are getting a little bit better, but still not great. Now actually things are getting a little bit better. I mean, so you're never going to have an amazing image. But one thing that you can notice, for example, and again, this is like crap on my screen. Now this little star is actually getting to be a lot brighter, right? And so, for example, if I were to see where it used to be over here, right? So the Wiener filter has kind of taken this blurry thing and it's kind of tried to sharpen it up into a nice round star. And if I keep on going, hopefully I can do a little better. Right, so now here's kind of the before and after, and here I can see that some things have gotten better, right? So again, if I look out into space here, I can see that I have this star that is definitely a nicer, compact, object than it used to be, and this doesn't seem to have very many of the artifacts that I had with lower values of K. If I also zoom in on this region here, for example, I can see that I've definitely made it a little bit less noisy, right? I preserved a nice edge. So I mean, this is about as good as I can do, right? I've definitely both denoised and de-blurred the image. In order to do it, I had to have a good estimate of the point spread function, and I also had to have a estimate of how bad the noise was. But even here, again, you can see kind of comparing the left and the right, this whole region on this side is definitely noisier in the original image than it is over here, right? So this is the kind of thing that people use in practice to clean up degraded images. And I don't have time to talk about it too much here. I'll do one quick thing here. So there's some very cool modern research on image processing that is kind of related to the Wiener filter, but also incorporates a lot of cool machine learning. And so let's see if there's an easy way to see some pictures here. So this is a paper that came out several years ago, but the idea is kind of related to the Wiener filter. So here I've got an original image, and here this is a problem that's specifically focused on the kind of motion that comes across when you move your camera when you're taking a picture, right? Because if you're taking a picture without a tripod, little micro motions in your hands cause the image to shake, and that can spoil, a normally nice picture. And so this is an automatic method for removing camera shake from an image, and it's kind of interesting because here again, this is an estimate of the blur kernel that's actually happening when you take the picture. So it's maybe not this nice Gaussian thing because of the way that your hand is moving and the amount of time that your arm stays in a given place. The actual blur kernel may be really funky. And I believe that they show that you can kind of see that from, I don't know if this is in this paper. There's this one great example that shows a scene where you can see from the motion of the lights what the point spread function should be. I guess it's kind of hard to tell. But anyway, you can kind of tell that, here's the difference between, I think this is the original image over here, and this is an image that is kind of like what we just did with the deconvolution with the Wiener filter, and this is an image that is taken, that is generated by the proposed algorithm, and you can see that this proposed algorithm is generating an image that's a lot sharper than the image that MATLAB is estimating. And so, again, you should look into this paper, and then there have been lots of follow-on work since then on automatic de-shaking of camera images. Here, there's definitely some, secret sauce going on in terms of applying deeper knowledge about the way that, camera shake occurs in natural images, whereas MATLAB doesn't know anything about image formation or anything like that. We're just applying the Wiener filter from straight signal processing theory. So this is kind of a very cool offshoot of, of computer vision research that is kind of relevant to our class. And so if any of you had thought of that as a project, it would have been a good project, but everyone's already decided on their project, so there. Okay, so any questions or comments?
If you cranked up the number in that function that you're doing, what would that?
Yeah, what would happen if I crank this up even more? So here is like saying that there's as much noise as there is image. So I'm not sure what I would expect to see, but we can find out. So here the image is getting a lot blurrier, right? So kind of what I'm saying to the Wiener, let me think about this for a second. So kind of what I'm saying to the Wiener filter is that there's a lot of noise in this image, and you should be aggressive about filtering it out, right? So things are getting flatter, I think is one way to think about this. And if I were to continue to say there's more noise in this image than there actually is signal, right, I'm sure that I would start to get something that doesn't make any sense, right? So here I've got basically something that's almost entirely, dark, right? Okay. So I think I'm going to stop there.